Okay, good morning. So I will review the status of axion dark matter searches, and in particular, I will focus in the role of quantum sensing and quantum technology in the axion detection. So I will give a brief review of axions and axion detectors. Then I will talk about results of experiments obtained with amplifiers. And finally, I will move to quantum sensing, giving some example of experiments and some more proposed counters, and finally the conclusion. So axions. In 1975, there was a problem related to the eta prime particle. There is a meson, like the pi on the cone, and the problem was its mass that was much larger, for instance, larger than the eta mass. So the reason was not due to the different content of quarks, and people realized that there was a broken symmetry. This was the axial symmetry, and so this was called the U1A problem. And realizing that there is a broken symmetry in QCD, this breaking was given by this term here, and that solved it, if you want, this problem. But then it arises a new problem that this term violates CP. The discrete symmetry charge parity. So if you have CP violation in a strong interaction, what you expect is that the neutron has an electric dipole moment. Now, experiment has been done to measure this electric dipole moment, and this resulted in a value compatible with 0, with a high accuracy. So if the neutron has a dipole moment, it is very, very, very small. Okay, so this means that this theta factor in this term, it's less than 10 to the minus 10. So again, we have a new problem because it wasn't natural and people couldn't understand why this theta factor was so small. And here came the idea of Roberto Pichey and Helen Quinn in 1977 to resolve dynamically the theta problem, introducing the axions. And an unexpected feature of axions is that once you introduce this particle in the evolution of the universe, you end up with a lot of dark matter. So you have a really nice candidate for dark matter. So there are many limits and experimental results on axions that come from stellar physics, from cosmology, and so on. They usually are shown in a plane where you put on this axis, on the vertical axis, you put the axion photon coupling, and on the horizontal axis, you put the axion mass. The yellow band is where you expect from theory, where you expect to have these axions, QCD axions. Okay. Now you see that there is only one class of experiment reaching this band in this region, and these experiments are called the haloscopes. And this is where I will focus my talk. So there are many haloscopes around the world, in the USA, in Europe. There is a larger center in South Korea and another one in Australia. And this is a picture of a cartoon of a typical CKV haloscope, let's say a state-of-art CKV haloscope. And it's a kind of a radio frequency and cryogenic antenna for dark matter, where you have a strong magnet with a usually 10 Tesla magnet, and inside it there is a resonant cavity resonated at gigahertz frequencies, And everything is put inside a dilution refrigerator at about 100 millikelvin. And the signal is amplified with an amplifier that usually they have a noise close to the standard quantum limit. That means one single quantum of energy. And there is a further amplification at room temperature. And finally, the signal is acquired, down converted, and the power spectrum is measured. And what we look for are deviation in power from the expected mean that at some frequency, that may be due to dark matter axions that just resonate in our detector. One important figure of merit of these experiments is the scan rate. The scan rate means how much frequency beam you can look at in a given time looking for axions. Okay, is how fast you go in frequency, like tuning your detector and looking for axions. And this rate depends on many experimental parameters like the magnetic field, the volume, the quality factor of the cavity, and then it is inversely proportional to the square of the noise, okay, the noise temperature. So it is fundamental in this kind of experiment to reduce the noise, to speed up the scan rate. Okay, so in this picture, I'm showing different kind of noise contributions that enters in a haloscope search. So you have in green the thermal noise. You have in red is the standard quantum limit. You see, this is a function of the frequency, and I report here different names of different haloscopes that they work at different frequencies, just to understand the different role the noise has in different experiments. And in blue, I'm showing what happens if you have a counter. Now, many experiments, I will show it now, are using amplifier that have a noise close to the standard quantum limit. So they have essentially this red curve noise. Now, it is important to understand how at higher frequency this noise can be very, very large. So only a counter can help and boost our detection sensitivity. So we'll review now the results obtained with the amplifiers. And this is ADMX in Washington University. It's a haloscope with an 8 Tesla magnet, 100 milli-K temperature, working at a frequency of about 1 gigahertz. And the first amplifier they use at the quantum level was a microstrip squid amplifier. And this is a technology that, while usually DC squid are limited to few up to 100 megahertz in frequency, to go higher in frequency, there was this new design where the input coil was replaced by a resonator. So you could go higher in frequency and have some kind of resonant curve in your gain. With this is the picture from this paper, and there is about 100 megahertz width and a 20 dB gain, and you see that at this 1 gigahertz frequency, as the temperature of the bath is reduced, the noise added by the amplifier goes to the quantum limit. But then soon experiments moved to another kind of amplifier. There is a Josephson parametric amplifier, and this is a quantum limited almost quantum limited amplifier, and that where amplification, parametric amplification is obtained with a Josephson junction, or DC squids, or array of junction. Essentially, there are two types of two families of amplifiers. There are full wave mixing amplifier, like in this case, where essentially you send a pump frequency that mixes with the signal and amplifies the signal, that has a frequency close to the signal frequency. In the other case, you have a three-wave mixing amplifier, in which the pump frequency has double the frequency of the signal. So ADMX soon moved to a Josephson parametric amplifier. You see pictures here. It is composed by a series of 5 DC squids, and it is a full wave mixing with a gain of 25 dB, 5 megahertz bandwidth, and a quite large tunability of about 500 megahertz. And you see in this picture below in orange the result obtained by the experiment with the squid, MSA squid, and in green the results obtained with the JPR. You see, for in this range of frequency, they go down with the sensitivity, excluding essentially in all the QCD band the axion existence in this region. Another, as I said, large laboratory that is in South Korea is IBS CAP, and they are working on 4 different alloscopes. You see the names here that work at different frequencies with different magnetic field and slightly different technologies. They already had nice result reaching the QCD band, and they started an R&D, a characterization of parametric amplifier. You see the picture here. This is a 3-wave mixing amplifier, in which you have a transmission line terminated by a DC squid, and with the flux on the other side, you pump the signal. So again, they reach almost the quantum limit, and at 2 gigahertz with a 20 dB gain. Okay, then another experiment is high stack. High stack is working at a frequency of about 6 gigahertz with a 9 Tesla magnet. You see the resonant cavity here and the dilution refrigerator. And here is a picture of the parametric amplifier. Again, it's a series of squids. And again, they reach 20 dB, almost the quantum limit, the 20 dB gain, tunability of quite large tunability of 2 gigahertz, and a bandwidth of few megahertz. And here is shown the result of high stack. So finally, we have a Quax in Italy. INFM experiment is working at 10 gigahertz with a 8 Tesla magnet at 100 milli-K temperature. And in the latest measurement, Quax reached the QCD band using a Josephson parametric amplifier of this kind. As a ring, you have a ring of Josephson junction. In this way, you can mix you can mix the 3 signal and have it resulting in a 3-wave mixing amplifier, and they reach a noise close to the quantum limit. So a different way of using parametric parametric amplification is squeezing the noise. This was done recently by Heisteig. This is the Nature paper here. And what you do before your cavity, you usually have some noise reflecting on your cavity, and combining with a signal coming from the resonant cavity. And so what they did is to use the parametric amplifier to squeeze. What does it mean? In one of the quadrature, you de-amplify, you squeeze the noise, and you amplify on the other side. Then the signal is reflected on the cavity and combines with the signal coming from the resonant cavity, and then the opposite procedure is done with a second parametric amplifier, in which you amplify in this case in the X quadrature, and you squeeze in the Y quadrature. So you end up essentially with the lower noise and larger bandwidth. Okay, and they succeeded in increasing the scan rate by a factor 2 with this technology. So, a nice way of using a parametric amplifier. So now one of the problems of experiments is the bandwidth. We would like to have not a 100 megahertz bandwidth or tunability, but have gigahertz, so we can scan more frequencies and look for a larger range of masses of axions. And so people now is looking to traveling wave Josephson parametric amplifier that are essentially transmission lines made of Josephson junction, in which you have the mixing of the pump and the signal. So you end up, like in this picture from this paper, in a very, very large range of frequencies, order of gigahertz, in which you reach the 20 dB amplification with the noise at the quantum level. Okay, so let me move now to photon counters. Let me remark the role of noise in the scan rate. So as I said before, to search in a larger mass region for axions, you have to be fast, no? Because you have to tune your detector, and the rate at which you can scan the frequency, it depends on this formula that is inversely proportional to the noise. So the lower is the noise, the faster you go, and also more sensitive you are. So you see that going to higher frequency, as for quarks, Mad Max, organ, also the standard quantum limit is a limiting factor. It's a strong limiting factor. And so you have to move to photon counters. And to be competitive with amplifiers, a photon counter must have a low dark count, so low noise, low errors in counting. And by low, I mean at least less than 10 kilohertz error. In this case, you see this curve here is for 1 kilohertz, and this one is for 100 hertz. So 100 hertz, you will have an order of magnitude improvement in the scan rate. So we had recently a publication on a result of not exactly on axion, but on dark photon, but it's, let's say, the axion-like particle, if you want, with a quantum sensor. And this is composed essentially of a storage cavity and a readout cavity, and the two cavities are bridged by a transmon. And what happens when you the spectrum, the frequency spectrum, the power spectrum of the transmon just reflects the number of photons you have in the storage cavity. So you can implement your your readout procedure to observe the status of the qubit from the readout cavity. And essentially, the main point of this experiment is that they have the photon lives in the storage cavity in a superconducting cavity, so has a very long lifetime, hundreds of microseconds. And you perform a quantum non-demolition measurement. So you can test many times, probe many times the presence of a photon. And so you can average out any readout error. And so as you can see in this picture, they reduce to essentially zero the probability to have an error with 30 measurements for a single photon. They reduce to essentially zero the probability to have a readout error. The other example I want to give is also a recent paper in which a qubit is put inside a cavity with a ferromagnetic crystal. This is a technique introduced by quarks, in which you exploit the interaction of axions with the electron spin. And so in this way, this group have an effective coupling of the qubit with the magnons inside this ferromagnetic crystal. And the device is so sensitive that can observe like up down to 10 to the minus 3 magnons root of Earth. Okay, so very, very sensitive. And with this, they made a prototype detector for detecting axion interaction with electron spin. But there are many papers on counters, many proposals. And one of these is using current bias Josephson junction, in which the arrival of a photon just triggers the transition of the junction from the superconductive to the resistive state. And this kind of detector has the potentiality to reach milliards Dark count. And another kind of detector is this one that is very nice, since with using this a two-cavity scheme where the cavity again are connected by a qubit, they reach the perfect matching, so that when there is an incoming photon, so not a photon already in the cavity, but a photon traveling in a waveguide, there is a perfect matching so that the photon is not reflected back. And so they increase the efficiency of the device. And they also reached a 1 kilohertz dark count, which, as I showed before, was the thick blue line. It's a very, very good, and it means already improving with respect to parametric amplifier. So finally, a few words about our project SuperGalax that has taken up the challenge of developing a quantum sensor with an extremely low noise and high efficiency, using a network of interacting superconducting qubits. And this device will be installed in our haloscope in infrastructure. You see the picture here. So I come to the conclusion. In the last decade, there was a lot of interest in axion and axion-like particles, and the major challenge is clearly the phase signal of this particle, so fraction of a yoctowatt in our detectors. And so I show you that now experiments are using quantum limited amplifier like JPA, and they are probably moving to traveling wave parametric amplification. But if you want to move to higher frequency, let's say 5, 10, 15 gigahertz, what you really need is a quantum sensor, so a single photon detection in the microwave. Thank you.